On number 76 from the binder, we are supposed to be working with the piecewise function for all the group underneath. And the two functions are both linear, it looks like. One's for x less than 1, or equal to, that is, and greater than 1. Okay, and in the number 76, they ask us for what is the value of f at 1. And remember, if I want f of 1, all I'm asking for is what is the function value at 1? What is the y value when we're at x equals 1? Well, we're defined at 1 with the top function, not the bottom. Okay? So essentially, we're just going to put the 1 into our top part of our function, and we're going to get 1, and that is the function value. Okay? You know, had this one been the greater than or equal to, and this one just been a less than sign, you know, then we would have put our 1 in here, and we would have gotten 1.5. Okay? But again, since it's defined to be 1 for the top part, then that will be our result. While we're on the binder, anything else from the binder before we move on to the book questions? Start there. That's in the binder? Anything else in the binder before we move on? And 72, it says the limit as x approaches 0 of x plus sine x over x is equal to 2. And the question is it true or is it false? Okay, that's what we're after, is whether it's true or false. And the direct evaluation possibility is no good here. True? Because if we put a 0 in there, we're going to get 0 on the bottom, so we can't do a direct evaluation at this point. And so the question is, can we do anything else in terms of algebra here? Well, one algebra technique that we could use is we could write x over x and sine x over x. That would be a valid algebra step here, wouldn't it? Okay. And what would that allow us to do? The x over x, that would become what? That would become 1. Okay. And if we did that, then we would have 1 plus sine x over x. Okay. And there is a special limit that I want you to take a look at right now in your book, which you find page 57. And on page 57, that special limit, this function sine x over x actually comes up from time to time. It's kind of a special function. And there's really no more algebra we can do with that. Okay? Ultimately, though, we're going to recognize that that particular function has a special limit. Okay? And the other thing that we have in terms of limits is that we're allowed to change when we have some kind of two-part expression, that we can write these both separately. One of our properties of dealing with limits. And ultimately, in this particular case, if we were to do a direct evaluation on this one, we would do the limit as x approaches 0 of 1. Well, think about what kind of function is 1. If I graphed y equals 1, that's what? That's a line. What kind of line? It's horizontal. Don't say straight. All lines are straight. Okay? Okay? So, ultimately, it'd be a horizontal line. So when we're at 0, our y value is still what? 1. When we're anywhere, our y value is 1. So the answer to the first part is 1. And then what does it say on page 57 about this special limit? That's also equal to what? 1. And therefore our final answer is what? 2. So therefore the actual final answer is true. Okay. Alright, so again, this special limit right here is just one that we, when we see it, just need to recognize that that's one that we know is always 1. If you were to forget that, but you were able to use your calculator, could you just graph that and see the fact that it's 1, or look at a table and see that it is in fact 1? Okay. All right. The other part I wanted to mention here at this point too, if you turn your page 58, okay, those properties of limits that I mentioned, if you did look at that when you were doing your reading, etc. Ultimately, just being able to do the limits separately on those two things is one of our nice properties of limits. We can do the same thing if we had a product of two functions. We could do them separately and then multiply Same thing with division. Of course, if we have two things that are being divided, the only problem is the 0 on the bottom possibility. We have a problem if that happens. And then the power rule, if we were to raise something to a power, like say we were trying to find the limit of x plus 2 to the 8th, let's say, and it says x approaches 2. Okay, we could, all that is telling us is that we could separate this, we could do the limit of x plus 2 and get 4, and then we could take that 4 and we could raise it to the 8th power, so we can separate those two operations. Okay? And so having those properties, that limit operation, and keep in mind that this limit really is an operation. It's just like adding two things. I mean, if I were to evaluate this and get an answer, which is ultimately 4 to the 8th, I don't know what the number is, but if I were to do that, okay, that limit statement is now gone. I evaluated it. The limit is just telling us to do something to this expression. Okay? Same thing, if I did 4 plus 4, that's equal to 8. Well, where'd the plus go? Well, it's gone because we did the operation. True? So that's why there is no, on the other side of our equation, there's no limit because we actually evaluated the limit. Okay? So the limit just tells us to do something. And like I said, the fact that it has these nice properties where we can do things separately, okay, makes this limit what we call a linear operator. Okay? And I won't ask you to necessarily repeat that at any point, but that's what it is. Okay. Anything else from the packet? Anything on what we've discussed so far? All right. How about the book questions? Was it 40 what? 3? All right, on page 43, we have some property problems. Again, they tell us that the limit of f of x as x approaches 4 is equal to 0, and the limit as x approaches 4 of g of x is 3. So those two pieces of information are given, and ultimately in part A, we need the limit as x approaches 4 of g of x plus 3. So this one is actually very similar to what we just did on that previous problem, because our properties are going to allow us to do these two limits separately. And once again, if you want to, you could write the limit of g of x plus the limit of 3. Okay, you can do that if you want to, or you can just know that that's the case and you can just handle the two limits separately. So what do we know about the limit as x approaches 4 of g of x? That's what? This part right here would give us 3. That was given. And then the limit of any constant, okay, we know again constant functions are horizontal lines, their y values don't change, so it's still what? 3, and therefore our answer for that one would be 6. When we have letter B, it says the limit as x approaches 4 of x times f of x. So once again, this one is a product situation. So if we were to separate those two into two separate limits, and I'll write it out this time since we didn't have one written out like we did in the previous one with the addition. So ultimately that would be our new statement if we use the properties correctly. And we'll just take the two limits separately and then multiply them together. So how about this one? What's our first step in evaluating any limit? Direct evaluation. So what's the answer? 4. And this one? I mean, I don't know what this function is. I want to put something in here. I don't know the function, but what I do know is I already know the answer to the limit up here. It's 4 times 0. So ultimately the answer to that one would be 0. Okay. Part C, similarly, if we have the limit as x approaches 4 of g squared of x. And remember, key piece of information, g squared of x, or sine squared of x, or ln squared of x. Remember that notation means the following. It means sine x all squared. It means ln x all squared. Got to make sure we're careful on order of operations here. If you see that notation, that means find the sine and then take the answer and square it. Same thing with natural log, etc. Those are two, any trig function is going to have that same notation. So ultimately, if we were to rewrite this as g of x squared, we can use that power property I just mentioned. We know that if it was just g of x, the answer would be 3 up there. And what are we going to do with that 3? We're going to square it, so therefore our answer would be 9. Questions so far? Finally, part D, so we can squeeze it on this paper here. We got g of x over f of x minus 1. And limit as x approaches 4 again. So this time, once again, the quotient rule works the same as the product rule. We can do these two, we can do it all separate, provided the bottom doesn't equal 0. So what do we know about the limit as x approaches 4 of g of x? It's 3. And the bottom, we know that these two would be a subtraction, so we could do those two separately. This one we know is 0. We know this one is 1. So 0 minus 1 will be negative 1. Final answer will be negative 3. Okay, questions on that one? Okay, what else from the book? Sorry.
C and D on 51.
All right, on 51 we have piecewise function again. 3 parts this time. 1 minus x squared is the first part, 1 and 2. And this is from 0 to 1. This is from 1 to 2. And it's 2 when x equals 2. All right. So when we take a look at a picture here, we're going to answer any questions about any limits. Okay. We can see that the domain here is essentially just from 0 to 2. There's nothing more than that in terms of our definition over here. So 1 minus x squared, if we were to recognize, hopefully we can recognize that as a half circle. Okay. If not, we have to plot some points here. If we put in 0, of course we get 1, so 0, 1 is a point. And if we put 1 in there, which is the other endpoint, we get 1 here. I'm going to currently put that as an open circle though, because notice 1 is not included for that particular function. Okay. So I'm going to leave it as that for the time being. And again, we would have that as our graph. And there's no reason you can't have a calculator at this point either. But I would start to recognize some typical functions, and you could obviously graph that and see that it's a half circle. But from here, they told us that between 1 and 2, so between 1 and 2, the function is 1, which means it's a horizontal line. So we'd actually be up here, go across here, open circle again, because 2 is not defined for that part. And then it jumps up to 2, 2, which would be another point right here. So essentially we'd have that as our picture. Alright, so with that being our function, if you look at, we'll say part C and D that you mentioned here, we got, says at what points C in this domain here does only a left-hand limit exist. Okay? So does only a left-hand limit exist. Okay? So in our, I guess in our picture here, if we look at any of the key points here, let's look at the interior points first. If we look at 1, the question is, does it have a left-hand limit? Is there a limit as we approach from the left? Sure, it's 0. Is there a right-hand limit? Just for curiosity's sake, because I know D is about right-hand limits. Is there a right-hand limit? Of course, it's 1. What about, and I guess that's the only interior point, because 0 and 2 are both on the edges here. Let's talk about as we approach 1 right here. As we approach 1, could we name a right-hand limit? Or, I said that backwards. As we approach 0, I should say. As we approach 0, could we name a right-hand limit? It would be 1, wouldn't it? But can we name a left-hand limit? No. So wouldn't x equals 0 be the answer to part D? Where there's only a right-hand limit? Okay. And then left-hand limit, as we approach 2 from the left, could we indicate a limit here? It would be 1. Even though they have 0.22, the limit is still 1, because that's where we're close to. Okay. And ultimately, it would only have a left-hand limit, because is there anything to the right of 2? No, there would be no right-hand limit there, so there would only be a left-hand limit at x equals 2. Good question. Anything else on number 51? What else? Alright, on 58, I'm going to tell you what the answers are, and then I'm going to have you raise your hand and tell me if you got it all right. Right? We'll see how our challenge problem was from yesterday. So, finding G, the answer for G should be 5/4. And the answer for part B, the average speed should be 5 meters per second. Who's still in? Good. And finally, part C, the instantaneous speed at time 4 should be 10 meters per second. Who's still in? No, good. Alright, not too bad. So ultimately, again, we have an equation here that gives us distance when we have this free fall situation. They told us that the rock hits the bottom at 20 meters, and that takes 4 seconds. So if we were to plug those two given information pieces in, we get 16 G. And if we divide, we get 20/16, which is 5/4. So ultimately, this equation now dictates all of our work, essentially, because that tells us the distances at any given time when this rock is dropping into the crevice or wherever it's going. Okay? Now, the average speed in this time frame, remember the average speed is the change in distance over the change in time. So our change in time, we know, of course, is 4. And our change in distance, we need to know how far down the crevice this rock goes in the 4-second time frame. Well, we can put a 4 in here, get 16, and multiply by 5/4 and get 20, but didn't we already know it was 20 because they told us it was 20? So ultimately, what was the change in distance over change in time? 5 meters per second. Alright. So ultimately, all that stuff could be done with pre-calc information. But what we're going to deal with next is what about that instantaneous speed? So, as we talked about yesterday, we want to use the point in question is 4 seconds. We want to know what's the speed at 4 seconds. Okay. We know that the point here is time, time 4 and distance 20. Okay, that's our point in question. We want to know the speed at that point. So we need another point that's very close to 420. We could use 3.9 and then some distance, and that would give us an estimate for what the speed would be at that point. We could use 3.999 and some distance and get an even better approximation. But to get the exact answer, though, we need to use a point that's infinitely close to 4, namely 4 plus h. Okay? And ultimately, we want to let that h become 0, because we want this to be as close to 4 as we can possibly get. So the question is, what goes into our y column here? Well, we want to know what is the y value for our function at 4 plus h. Well, it's 5/4. 4 plus h squared. Because the time in question in that second point is 4 plus h. So, next issue, now that we have the 2 points established, is find the slope between those 2 points. So if I write 5/4, 4 plus h squared minus 20 on top, and then 4 plus h minus 4 on the bottom, and I have it set up correctly so far. How about the questions at this point before we carry on to the algebra part? Alright, on the bottom we can see fairly clearly that the 4's are going to cancel out and we'll have h only, which is good because that's what happened yesterday and seemingly that's what should happen, right? So on the top, if we do 5/4, and then we do 16 plus 16h, oh, I lied, 8h, plus h squared minus 20, all over h. Expand that 4 plus h. And did anybody read the syllabus that I sent where it says about the pre-calc syllabus? Anybody know what happens if we just write 16 plus h squared here? That's one thing. Nobody read the syllabus yesterday like I asked? You see up there on the board it says don't get hit by the train. That's what it says in that pre-calc syllabus. It says if I'm going to show a video of somebody writing 4 plus h all squared equals 16 plus h squared and then getting hit by a train. So don't get hit by the algebra train. Do not just square the 4 and the h because that is not the correct answer. This is a binomial, so we need to write it twice and FOIL it and get our true answer, which is 16 plus 8h plus h squared. So once we do that, we can distribute the 5/4 And I'm gonna go over here, I run out of space here, and we get 20, which, why is that good? Because we got another 20 over here that's gonna need to be gone in order for us to do anything with the h's. 5/4 times 8 is 10, so we get 10h. And then 5/4 h squared minus 20. And all said and done, we would cancel the 20s, factor an h out of the two-part expression we have on top, the binomial. And if we did that, essentially we're canceling h, and the squared, so we just have an h in that one. And we wind up with an expression 10 5/4 h. And remember, all the while here we're taking the limit as h approaches 0. So once we get down to this expression, now we can finally directly evaluate. And if we put a 0 in here, we get 10 plus 0, which is what? 10 meters per second. Alright. Questions on any part of that process? If you don't feel like you have that process down completely at this point, it's okay, because this process is going to be used quite often. We'll use it a lot more. We'll revisit it later in the chapter, and then also chapter 3, we'll be using it quite a bit. Okay. All right, how about anything else on this one before we move on?